Hello everyone, my name is Jia Su. I'm going to present our recent work, CapelliniSpTRSV, a thread-level synchronization-free sparse triangle solve on GPUs. This is a joint work of the University of China, China University of Petroleum, National University of Singapore, and Illinois Institute of Technology. This is the outline of our presentation. Next, I will introduce the background. First, let me introduce the matrix format. If the majority of elements in a matrix are zeros, we can store the matrix using a sparse representation that only requires non-zero elements. The compressed bar row format stores a matrix in row-wise with 3 arrays without zero values. The matrix in Figure A can be stored in the format of Figure B. The CSR row pointer arrays store the beginning position of each row. The CSR column index array stores the column number of each element. And the CSR value array stores the values. Next, I will illustrate the sparse triangle solve. For sparse triangle solve, it computes a dense solution vector X from the sparse linear system, where matrix L is a square lower triangular sparse matrix, and B is a dense vector. Then, I will introduce the basic concepts that are essential for understanding sparse triangle solve. For the equation set Lx equals B, we provide the following concepts. Component is an element in solution vector X, such as x0. Element is a non-zero element in matrix L, such as L00. Dependency: if the solution of component xi needs the value of component xg, xi has a dependency on xg. For example, due to element L21, the component x2 needs the value of component x1, so x2 has a dependency on x1. Level is a solution order according to the dependency among components. The components at the same level from a level set. Next, let's review the current sparse triangle solve algorithms. I will show the level set algorithm in this slide. The level set method has 2 phases. The first is grouping nodes according to their rows or columns that can be consumed in parallel. The second is solving nodes group by group with barriers between. This is the warp-level synchronization-free sparse triangle solve proposed by Liu and others in 2016. The algorithm computes the component X in the original row order of the input matrix and uses one warp to compute one row. And it adds a new flag array in degree to show whether the component X is solved, which avoids the synchronization and greatly reduces the processing time. In addition to the 2 algorithms mentioned earlier, NVIDIA cuSparse library also provides functions for sparse triangle solve directly. We summarize the differences between the 3 algorithms and test their performance with 3 random sparse matrices. As shown in this table, we can observe that the synchronization-free sparse triangle solve algorithm exhibits short pre-processing time and high performance. In comparison, the pre-processing time of the level set sparse triangle solve algorithm is very long, which greatly limits their applicability. However, we find that the current synchronization-free algorithms does not fit all situations. We define a new indicator called parallel granularity to describe the matrix characteristics for sparse triangle solve. In the equation, n level means the average number of components per level, and n0 means the average number of non-zero elements per row. The performance trend of warp-level synchronization-free sparse triangle solve is shown in the figure. As the increase of parallel granularity, the performance increases at first, and then declines. The reason is that As the parallel granularity increases, the GPU resources are underutilized, more idle states are pairs in threads, and insufficient GPU parallelism happens. A thread-level synchronization-free sparse triangle solve could help when the performance declines, which is our motivation. We use this slide for further explanation. In this figure, we use rectangles of different colors to represent different layers. Pink rectangles represent level 0, yellows represent level 1, blues represent level 2, green rectangles represent level 3, and orange arrows represent the data dependency. For simplicity, we assume the GPU device can launch 2 warps at the same time, and each warp can support 3 threads. In Figure A, which is the level-set sparse triangle solve, although it can execute at thread level, the synchronization in the level-set design limited its parallelism. In Figure B, which is the warp-level synchronization-free algorithm, it achieved performance improvement by removing synchronizations compared to Figure A. There are still many idle threads. Figure C is our thread-level synchronization-free sparse triangle solve. Our new design utilizes the GPU better, but there exists inter- and intra-warp communication. Previous synchronization-free designs are mainly based on warp states and synchronization between warps, but ignore the thread states in warps. Hence, we call such warp-level sparse triangle solve coarse-grained. In contrast, we additionally consider thread states and thread-level synchronization within warp, which is fine-grained, just like capellini, a very slender kind of Italian pasta. Then, I will show the 3 challenges of our new algorithm. The first one is to avoid deadlocks. Previous methods are usually use a while loop to constantly check whether the relative value have been updated. Because the threads in a warp of the warp level algorithm are designed to update the same value, they do not have deadlocks. However, in thread level design, the thread in one warp may have dependency. For example, in our program simply compute all elements before updating the component. Then thread 2 and 3 in the figure showing called deadlocks. Because thread 2 and 3 are in the same warp, when thread 3 constantly check x1 for the element L21. According to the GPU lockstep manner, thread 2 also executes the same instruction, but does not update the status of x1. The second challenge is the last element checking. In sparse triangle solve, when processing a non-zero element in a row, we need to verify whether the precise element is on the diagonal. A common solution is to add an if statement for checking the last element before processing each non-zero element. However, such last element checking causes runtime overhead. For example, in the process of thread 5 in the figure, last element checking happens before thread 5 processing the element L40 and L41, which should be removed. In our experiment, this overhead can cause 27.3% performance slowdown. The third challenge is thread execution model. Although we use a thread to handle one component, the GPUs are still executed in the warp execution mode. In the detail, the threads in the same warp have to transmit the required components simultaneously. For example, thread 6 requires x2 for computing element L52, which can only be obtained after the third cycle. However, if we simply use a while loop to check the condition to move on, thread 6 starts this checking from the beginning, and thread 4 and 5 within the same warp also need to wait for thread 6 in the constant condition check, which means that the processing of L31 and L40 are also need to be postponed to first cycle, although their required x1 and x0 are ready at the second cycle. The first part is the data of our novel algorithm, CapelliniSpTRSV. I will show our three new designs in Capellini to solve the challenges mentioned before. First, we propose a two-phases mechanism to avoid deadlocks. We divide the computation process of a warp into two phases. The first phase is for the element in the related row of matrix L that has no interdependency within a warp. After calculation the element without interwarp dependency, we compute the interdependent element in the second phase. Second, we propose a novel design to reduce the number of last element checking. First, I will introduce the two functions marked in red before. In the first phase, the element without interdependency can be processed directly and do not cause deadlock problem. So, we use a traditional busy waiting strategies to compute the elements, which shows in function process while loop. In the second phase, since threads in the same warp execute synchronously, the traditional busy waiting method cannot be used. Instead, the threads have to check the finishing conditions. To reduce the number of checking, we find that if the function checkSwap is true, the element must not be on the diagonal. Thus, we only need to check the elements whose relevant components are not ready. Third, we propose a writing-first optimization that threads can compute the element and write the partial result first without waiting for other threads. We remove the computing part in the first phase and expand the scope of the second phase computation from the interwarp-dependent element to the whole element in the row so that thread can compute the element and write the partial result first without waiting for other threads. Our algorithm has the following desirable features. First, no preprocessing. CapelliniSpTRSV does not involve any preprocessing, so that our algorithm can easily apply to various situations. Second, strong effectiveness. By addressing the limitation of existing approaches, Capellini supports sparse matrices that have high parallel granularity, which enable the synchronization-free sparse triangle solve design to efficient for various sparse matrices. Third, the compressed spiral format. Capellini adopts the most popular compressed spiral format, so that users do not need to conduct format conversion. The fifth part is evaluation. For methods, Capellini represents our novel algorithm. SynchroFreak represents the state-of-the-art warp-level synchronization-free algorithm, and Sparse represents the sparse triangle solve in Sparse. Besides, we measure the performance on three experimental platforms, including three generations of NVIDIA GPUs, Pascal, Volta, and Turing microarchitectures. We measured 245 matrices from the University of Florida Sparse matrix collection for validation. The average number of non-zero elements per row in those matrices is 19.6. And the average number of components per level is 12,484.9. On average, Capellini achieved a performance of 6.84 Gflow per second, while SynchroFree and Sparse only achieved 1.78 and 1.92 Gflow per second. Capellini achieved the highest performance for 87% of the matrices. We show the performance results for different algorithms on various GPU platforms in the figure. We show that CapelliniSpTRSV brings significant performance benefits. Besides, CapelliniSpTRSV achieves 4.97 times speedup over the SynchroFree and 4.74 times speedup over the Sparse. We show the performance speedup of Capellini over SynchroFree in the figure, and we can see that the performance benefits increases along with the parallel granularity. Specifically, at the parallel granularity of 1.17, For the matrix LP1, Capellini reaches an average 34.77 times performance speedup. In addition, we show the optimal algorithm selection between Capellini and synchro-free under two factors: the number of non-zero elements per row and the number of components per level in the figure. We can see that CapelliniSp triangle solve is the best choice when the number of components per level is high and the element per row is low. To further analyze the benefit of Capellini, we performed a detailed performance analysis. This figure shows the bandwidth utilization. We used the NVIDIA Performance Analysis tool, NVPro, to obtain the DRAM read and write bandwidth. CapelliniSp triangle solve achieves an average bandwidth of 56.09 GB per second for the matrices whose parallel granularity are larger than 0.7. The bandwidth utilization of Capellini is 5.17 times higher than synchro-free and 5.25 times higher than Sparse, which proves the effectiveness of CapelliniSp triangle solve. Besides, Capellini launches fewer warps than the previous synchro-free, and our algorithm is more concise. We measure the number of GPU instructions executed and the percentage of instruction stalls to exhibit the instruction execution of different algorithms. Figure A shows the number of executed instructions. In general, Capellini saves 76.02% instructions compared to synchro-free, and 56.02% instruction compared to Sparse. Figure B shows the instruction stall percentage. The value of our Capellini is 12.55%, which is 25.6% lower than synchro-free and 65.6% lower than Sparse. CapelliniSp triangle solve is already open source on GitHub. Currently, it has already drawn some attention. Here is our conclusion. We show our insights in current Sp triangle solve algorithm and propose parallel granularity to describe sparse matrices. We develop CapelliniSp triangle solve to precise sparse matrices that previous algorithms cannot handle efficiently. We evaluate CapelliniSp triangle solve with 245 matrices and demonstrate its benefit over the state-of-the-art Sp triangle solve. Thank you for your listening. I'm glad to answer any question.